Good afternoon, I'm Mr. Ish. Thank you for joining me for this video where we are talking about polarity and physical properties. This whole interrelationship between the two is very well demonstrated using organic compounds, especially carbon atoms and molecules which involve carbons. You want to start by looking at the covalent bond, which you know represents a sharing of electrons. Sometimes that sharing is equal, sometimes that sharing is unequal based on electronegativity differences with the atoms that are involved. When you're looking at covalent bonds, the atoms are trying to fill their octets by means of sharing of those electrons. You have polar and non-polar. And the difference between these two is due to electronegativity. If you look at something which is H and F, hydrogen and fluorine, or you can say hydrogen and oxygen, you can even say carbon and nitrogen. These are all atoms with differing electronegativity, so the bond between the two is a polar covalent bond, always in the direction of the more electronegative atom, as you know. So you have a dipole moment that develops, an unequal charge distribution. When you're looking at non-polar, you're looking here at compounds or molecules where you have equal electronegativities between the atoms that are forming that bond. Carbon, 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 hydrogen, oxygen, oxygen. Sometimes you can have dissimilar atoms, but their electronegativities are kind of the same, so they're considered non-polar. These are examples of non-polar covalent bonds. Anyhow, here you can have equal charge distribution, or you can have cancellation of dipole moments. You can also look at everything now with regards to the entire molecule. You can have a molecule which has covalent bonds which is polar in general, or it's non-polar in general. Think about this molecule as a whole. You have water, you have a charge being pulled towards the more electronegative oxygen. The dipole moments are in the direction of oxygen, hence you have a net dipole moment upward. So this here is a polar molecule made of covalent bonds. You can have another organic molecule or a covalent bonded molecule, or another compound or molecule made of atoms with covalent bonds, but they could be polar covalent bonds, but the molecule in whole or the compound in general is non-polar. Think about carbon dioxide. You have here carbon being attached to more electronegative oxygen. The dipole moments are in opposite directions, but this is a linear symmetric molecule. Everything cancels out, so this ends up being non-polar. When you're looking at everything, you're always looking with regards to the polarity of the bonds and then the polarity of the molecule as a whole. So keep that in mind as we look at everything in this video with regards to the physical properties. What can be some good physical properties we can look at? How about this? Boiling point could be one, melting point can be one. We can have vapor pressure. You know what vapor pressure is. Every liquid you put here in a beaker has a certain pressure above the surface of that liquid. The tendency of the molecules to go from the liquid phase and enter into the gas phase, and then those molecules will generate a certain pressure, and that right there is vapor pressure. It depends partly on the interactions of the molecules in the liquid phase between those molecules itself, the intermolecular and the intramolecular interactions, but it also depends on the volatility of that liquid or the compound that you're looking at. Let's look at everything here with regards to four compounds which all have a relatively same appearance and or the same number of carbon atoms. The only difference being this right here will have two oxygens. At the very top we're looking at a compound which is dimethyl ether. It's an ether compound. Then we have an aldehyde, and this right here is acetaldehyde. Here we have ethanol, it's an alcohol compound. Then we have acetic acid, which is an acid, but it's an organic acid. We're looking at everything with regards to these, and if you want to talk about something else, we can. As we talk about each of these, we can bring those other properties up. We look here at everything starting with ether, and you want to think about everything with regards to polar covalent bonds. You'll see polar covalent bonds in all of these compounds. Wherever you have oxygen combining or attached to carbon, or we have oxygen attached to hydrogen, you have a polar covalent bond. Wherever you have carbon attached to carbon, as you do here, here, and here, you have non-polar covalent bonds. So think about everything here with regards to polar covalent and non-polar covalent bonds, but generally the polar covalent bonds will affect the physical properties. You're looking at non-polar covalent bonds, but you see you have something like oxygen, carbon, and then you have the hydrogens attached to that. We don't have to draw them all. But you have a net dipole towards oxygen, net dipole towards oxygen, and they cancel each other out. It's very much like carbon dioxide. You end up seeing something here which is generally a non-polar molecule. Because it's a non-polar molecule and you don't have any ability for hydrogen bonding over here, because there's no OH, there's no oxygen bonded to a hydrogen, you have a compound here which will have the lowest from all of these, lowest boiling point, you'll have the lowest melting point, but it will have the highest vapor pressure because it will be most volatile. The lack of hydrogen bonding in this compound or in a liquid of this compound means that you'll have weaker intermolecular interactions. The compound will be more volatile and it'll enter the gas phase more easily. Therefore, it will be having the highest vapor pressure from all of these. It will indeed be water soluble because these carbons on each side are not too large. You still have oxygen. Oxygen can interact with water molecules and it can be water soluble. But from all of these four, in terms of boiling point, melting point, it will be the lowest. In terms of vapor pressure, it will be the highest because it will be most volatile. When you're looking here, you have a carbon, oxygen, hydrogen. And also keep in mind, as I was saying, this right here is non-polar, but this right here is a polar compound. You will have here a compound which will have a dipole moment in the direction of oxygen. There's an asymmetric charge distribution, and hence it's a polar compound, but it's not a very extremely polar compound, but it is much more polar than ether. That polarity makes this compound then have a certain higher boiling point, a certain higher boiling point, a certain higher melting point. Remember, boiling point and melting points are similar. If one is high, the other one is high for that specific compound. The vapor pressure will be slightly lower, not significantly lower, but it will be slightly lower. It will also be water soluble. This is water soluble, this is water soluble, because the oxygen here can interact with the water molecules easily. It's water soluble. This right here now has something that stands out clearly. It's a hydroxyl group, OH group, so it can do hydrogen bonding. The hydrogen bonding here will make it have strong intermolecular interactions. As a result of those hydrogen bondings and the fact that you have a polar molecule with a dipole moment here in the direction of oxygen, you will have here a higher boiling point. You'll definitely have a higher melting point and you'll have a lower vapor pressure because it'll be difficult for this molecule to be volatile because of the hydrogen bonding. The other alcohol molecules or the ethanol molecules will want to keep this in the liquid phase by means of that hydrogen bonding. And you can see that very well. You have a polar covalent bond right here between carbon and oxygen. You have the ability of hydrogen bonding. When you're looking at it, if R represents CH3, CH2, we're looking at something like this, my ethanol. It can now easily interact with other ethanol groups by means of hydrogen bonding. You can see all of that come into play, and it's not very difficult to envision that. You see all of these hydrogen bondings. You're not seeing hydrogen bonding in the ether and the aldehyde, but you're certainly seeing it in alcohol. Because of this hydrogen bonding, it'll have a very low vapor pressure and it'll have much higher boiling points and melting points in these upper two compounds, all as a result of the hydrogen bonding. The polarity of the compound in general and the electronegativity difference between the carbon, oxygen, or the oxygen, hydrogen certainly leads to these higher boiling point and melting points. Now this acetic acid is very much like the alcohol. It can do all of the hydrogen bonding as I was showing you before. I won't redraw it, but you can see it. It'll certainly have the hydrogen bonding because it has the OH group. But it has two oxygens. It will have from all of these the highest molar mass, and it will also have the highest density. Why will it have the highest density? Because if you put all of these in terms of the same volume, this will have more mass for that given volume because it has a higher molecular weight or higher molar mass. Because of the higher density, it will certainly have that higher boiling point and melting point, which also is a result of the hydrogen bonding. From all of these four, this will have the lowest vapor pressure because it will be most dense. It will be most difficult for this compound simply because of it having higher molecular weight to go from the liquid molecules into the gas phase. It will be just difficult for it. This compound will certainly have from all of these the highest melting point, the highest boiling point, the lowest vapor pressure, the highest density, and from all of these it will be the most polar compound. When you're looking at all of these with regards to polarity and physical properties, now we have a very good trend. When we're coming from up to down, you can see as you're going downwards, the hydrogen bond capability increases, the polarity increases, the boiling point increases, the melting point increases, and the vapor pressure decreases, the density increases. Looking at all of these four compounds and the trends we've seen, we can come in terms of a summary at two very good relationships. The polarity of an organic compound or any compound is directly proportional to melting point and boiling point. For the compounds which are being compared to one another, it is inversely proportional to vapor pressure. As the polarity will increase, the melting point, boiling points will increase, and the vapor pressure will decrease. As the polarity will decrease, the melting point and boiling points will decrease, and the vapor pressure will increase. So keep that in mind as we now come to the end of this video. Thank you for watching.